Okay, welcome to our notes on electric potential. This is really, it's kind of the bridge between an electrostatics topic and a circuits topic. This is going to be crucial for understanding circuits. In order to understand electric potential, we're going to go back and we're going to talk about electric field. What is an electric field? This was a kind of a tricky concept from the electrostatics part of this unit. An electric field is, at its most basic level, it is a change or alteration or warping in the space around an electric charge. Electric charges have this property that they actually change the space around them to make other electric charges respond to them. This is how they can cause forces on things that they're not actually in contact with. Now, we drew electric field lines to show the direction of electric field at different points. We also talked about the strength of an electric field. So what does that tell you? What does it mean when we talk about the strength of an electric field? An electric field has a strength of 1,000, and the units, well, because I say think about the units here, an electric field with a strength of 1,000 newtons per coulomb. Those are the units. What does that mean? What is a newton per coulomb? What information does that really tell you? Well, I mean, anytime you have one unit divided by the other, really what it boils down to is this. How many newtons of force act per coulomb of charge on object that experiences the electric field? How many newtons of force act per coulomb of charge on an object that experiences the field? One of the very first things I talked about with electric charge is that the more charge an object has, the greater the electric effects on it. So it makes sense that for an object with more charge, it would have a greater force on it. That's what the electric force tells you. How many newtons of force are going to act per coulomb of charge? If there's more charge, there's going to be a bigger force. To illustrate this, let's consider a set of oppositely charged parallel plates. We've seen those before, that create an electric field of 100 newtons per coulomb between them. The electric field intensity of 100 newtons per coulomb tells you that for each coulomb of charge, for each coulomb, that's capital C, of charge in the field, 100 newtons of force acts on the charge. So for example, if in this electric field, actually let's draw the electric field, it's a set of parallel plates. We talked about how the electric field is uniform for the space in between a set of parallel plates, and what that's going to mean is that we have evenly spaced arrows here showing the electric field. There we go. Electric field lines always point from positive to negative charges. That's what the electric field looks like for a set of parallel plates. If the positive is up here, negative is down here. So if you were to stick, let's say, a 1 coulomb charge in this field, that would lead to a force on that charge of 100 newtons because it's a 100 newton per coulomb electric field. If you put a charge of 2 coulombs in the electric field, it would experience a force of 200 newtons. If you were to put a force or a charge of 8.5 coulombs in, guess what? 850 newtons. Okay? It's kind of like a unit price. Unit price tells you the price per item. The electric field tells you how much force is going to get put on based on or per the amount of charge. So what's going to happen if we put that 1 coulomb charge in here and then we let it go? Well, if there's 100 newtons of force, since it's 100 newton per coulomb electric field, that's going to be a constant field all the way through here. It's going to be a constant force. So that 100 newton force is directed in what direction? If it's a positive 1 coulomb, if it's positive 1 coulomb of charge, it's going to be repelled from the positive plate, go towards the negative plate. Is directed toward the negative plate, and the charge will accelerate. in that direction. It'll accelerate towards the negative plate. And think about that for a second. If it accelerates, that means it's going to gain velocity. If you started off from rest here, it's going to speed up and speed up and speed up. Well, if it speeds up, doesn't that mean that the kinetic energy is going to change? It absolutely does. And you might say to yourself, well, why is the kinetic energy changing? Whenever you think of a changing amount of energy, you should think about the work that's being done, because work is the change in energy. You know from previous topics that when a force is applied to displace an object, there's an electrostatic force on this charge as it moves over this displacement. That tells us that work is done. There's some sort of energy transfer going on here. In this specific case, when the 1 coulomb charge is placed near the positive plate, when it's up here, it has a type of energy that we have not talked about yet. It has what we call electric potential energy. Remember, potential energy in general is energy that an object has that, if conditions change a little bit, can be converted into something else. It can be converted into, let's say, kinetic energy, which is the energy associated with motion. So it acquires electric potential energy just by virtue of being a positive charge near these other positive charges. When it's released, the electrostatic force does work on this charge. It starts to move down through some displacement. That original electric potential energy is now going to be converted into kinetic energy as it moves toward the negative plate. Starts off at rest, speeds up as it goes down. So if we want to draw a little diagram here, when the particle is up here, it has very high, and I'm just going to abbreviate, electric potential energy. After a little while, that particle has moved down to approximately here. So after release, the electric potential energy starts turning into kinetic energy. And as it continues to move down, when it just about has reached this plate over here, now all electric potential energy has turned into kinetic energy because of the work done by the electrostatic force, Fe. The electrostatic force has done work to turn the electric potential energy into kinetic energy. Now, imagine that we were to put more charge in here. Okay, we repeat the experiment, but instead of just 1 coulomb charge, we put 2 coulombs of charge in. Well, that's going to cause a bigger force, and because the force is bigger, the displacement's the same, you might say, well, more work is done. And if more work is done, that means more energy is transferred. So you could say that there's now more, that at the beginning, there was more electric potential energy, and at the end, there's more kinetic energy. If there was less charge in there initially, there would be a lower electric potential energy up here and a lower kinetic energy down here. So the amount of energy that's actually transferred and the size of the force, they depend on the amount of charge. We kind of talked about that with the electric field up here. The bigger the charge, the bigger the force. And it also turns out the bigger the charge, the bigger the change in energy. Well, what we want to know, what's more useful to us than studying just how much the energy changes for each different type of, each different amount of charge you could put in here, is if the energy changes based on how much charge is in here, is there a way that we could determine just a value for how much energy changes per charge? And it turns out that there is. We're going to define this thing called electric potential difference. This is going to be related to electric potential energy. We actually don't really talk about electric potential energy too much. Electric potential difference is related to electric potential energy, but it's not quite the same thing. Here's the definition. It is the change in energy or work done per unit of charge there we go, per unit of charge between 2 points in an electric field in an E field. Kind of a wordy definition. Like I said, electric field is a pretty hard concept to get your mind wrapped around. This one is on the same level. This one is also a little tricky. The change in energy or work done per unit of charge between 2 points in an electric field. So going back to our example here, how much did the energy change from here to here? In other words, how much electric potential energy did it lose, or how much kinetic energy did it gain? How much work was done between here and here, divided by the charge. Because remember, the more charge, the greater the energy. What we're trying to do is kind of like find the rate of energy transfer per charge. Okay? So it's how much work is done, how much energy is transferred, divided by what the charge on the particle is. And that should be the same no matter what type of charge we put in here. It's actually a characteristic of the plates, not a characteristic of the charge that gets put inside. It's a characteristic of the plates. We could say, no matter what sort of charge is in here, what the electric potential difference is between this spot near the positive plate and this spot near the negative plate. Just like an electric field is not going to depend on this charge as it moves from here to here. It's going to be a constant electric field throughout. It's also going to be a constant electric potential difference, no matter what sort of charge we put in here. One of the tricky things that students find about electric potential difference is that there's a million names for it. Okay? Informally, this is known as voltage. And there's other names as well that are variations of electric potential difference and voltage. You will hear me call this electric potential difference. You'll hear me call it electric potential. You'll hear me call it a potential difference. You'll hear me call it voltage. You'll hear me call it voltage difference. There's a lot of different phrases that all more or less at this level mean the same thing. One of the key things is that it's a difference, okay? It is a difference in this thing from here to here. When we talk about the voltage difference of, let's say, 6 units, I'll get to the units in just a second, we're talking about literally a difference in this thing from here to here. That's the key. The key is the difference, the change in energy between 2 points in an electric field. And I do also want to point out this word potential. You guys are used to using the word potential as an adjective to describe something. In this case, potential is actually a noun. It is a thing that you can measure. Okay? It is a difference in the electric potential. Okay? Electric is the adjective here. Potential is our noun. So, a couple of facts about electric potential differences. Positive charges move from high electric potential, which for positive charges means near other positive charges, to low potential. Which means far away from positives or near negative charges. There is an equation for the electric potential difference for calculating what this difference is. And it's kind of given right in the definition. Work done per unit of charge. If I go to the electricity page, page 4, in our reference tables, it is the next equation down that we haven't used yet. V, which is a symbol for potential difference or voltage or electric potential difference, equals W, work, or electric potential energy, divided by Q, where Q is charge. V equals W over Q. The definition is just the wordy version of this. Now, electric potential difference can be positive, can be negative. We're primarily going to deal with positives just to make it easier. It is a scalar, though. It doesn't have a direction. Okay, it's either an increase or decrease in electric potential. And the units, well, the units of work are joules, units of charge are coulombs. So the units are joules per coulomb, or V, which is volts. Okay, so this can get a little confusing sometimes to some people. The variable V stands for electric potential difference, informally called voltage, and the units are also capital V volts. And just a clarification in this equation. In this equation, Q is the charge moving through the field. It is the charge having work done on it. Now, really quickly, before we get into some examples, I do want to give you kind of an analogy. You'll notice that objects usually don't, it almost seems like objects don't want to have potential energy. If you think about an object that has gravitational potential energy, it only has gravitational potential energy because it's up very high, and given some changes, it will give up that gravitational potential energy and convert it to kinetic energy. An object, or like a spring that has elastic potential energy, wants to go back to its unstretched length. It has potential energy because it's either stretched or compressed. So since it's either stretched or compressed, it wants to go back to its unstretched length. That would give up its potential energy and change it to kinetic energy. Electric potential energy is the same thing. When charges have electric potential energy, that means they're near other charges of their own same type. Those types of charges want to repel each other. They want to get away from each other. So object that has high electric potential energy wants to get rid of that electric potential energy and convert that energy into kinetic energy. That's what we're talking about here. That's why something would move from here to here. You'll notice that potential energy, I don't want to say temporary, but objects want to lose their potential energy. They want to gain kinetic energy. Electric potential difference is kind of like, you can imagine like elevation. Okay, it's kind of like elevation change. You can think of areas of high electric potential energy as like higher elevations. You can think of areas of low electric potential energy as areas like lower elevation. So high electric potential is kind of like a mountaintop. Low electric potential is like a valley. If you have an object that starts off on a mountain, it's not going to go higher up the mountain all by itself. If anything, it's going to go down towards the valley. Why? Gravity is going to pull it down. It loses gravitational potential energy and gains kinetic energy. It's the exact same thing with electric potential. A positive charge that has high electric potential energy is near other positive charges. It's not going to go even closer to those positive charges by its own. It's going to want to go away from them. So it goes towards low electric potential energy, which is either far away from the charges or near negative charges. Okay, let's get to some examples. First one. A positive 3 coulomb particle loses 15 joules of potential energy as it moves from point A to point B, away from a stationary sphere of unknown charge. A, what kind of charge is on the sphere? Draw the electric field surrounding it. Well, if the particle at A is moving away from this charge, and this charge is positive, what must this be? Well, if this was negative, it would attract A. It must therefore be positive if it's causing A to repel away from each other. And since it's an isolated positive charge, we're going to draw an electric field surrounding it. That's very easy to do. It is simply electric field lines going straight out from the object like so. Straight out. Just like that. Now, what is the potential difference between points A and B? Well, since this is a positive charge and it's near another positive charge, this is an area for A because of the electric field from this charge where there is high potential. Regardless of if A is here or not, there is high electric potential here. Once you bring A, now A, once it's in this location, has high electric potential energy. A wants to go to where there's lower potential energy. So it starts at a place where there's high potential and goes to a place where there's low potential at point B. Okay? So notice that even though A has to be here in order for A to have some energy, even if A wasn't here, we would still call this area an area of high potential because it's close to this positive charge. Over here, farther away from the charge, there is low potential. So the charge, or the particle, loses electric potential energy and gains kinetic energy as it moves away from the like charge. We can calculate the potential difference between these 2 points by using the equation we just learned, V equals W over Q. The work done, it says 15 joules of potential energy was lost. That means the work done was 15 joules. So 15 joules. The charge is 3 coulombs. 15 divided by 3 is 5 joules per coulomb, or we could just as easily say 5 volts is the potential difference. And again, I just want to emphasize that this is a difference. 5 volts is the electric potential difference, the difference in electric potential from here to here. Another way of saying this is that B is 5 volts lower potential than A. And again, just to kind of recap everything that we're talking about, when we say that we're talking about electric potential, we're talking about the energy in the charge divided by, or the energy that the charge has divided by how much charge there is here. Okay? It's kind of like these charges, it's like they're carrying energy, and the bigger the charge is, the more energy it can carry. We want to know how much energy each unit of charge is carrying. That's what we're looking for here. Okay, so B is 5 volts lower potential than A. And that potential, we've kind of defined this potential as existing because of this electric field. It's the difference in energy per charge between 2 points in an electric field. Now, how much work is done if the particle had a charge of positive 5 coulombs instead? Well, we can use this equation. We now know that the potential difference between A and B is 5 joules, or 5 volts. That doesn't change if we change the amount of charge that the actual particle here that is moving has. It might change if we change the size of this particle. But the potential difference, the electric potential difference between these 2 points is established by this charge, okay? Not by this charge that's in here. So like the electric field, electric potential is based on the big charge, or the charge creating the field. Not the moving charge. So V, the whole point of saying that is V is going to be the same no matter what charge I put at A and move to B. The voltage difference, the electric potential difference from here to here is going to be the same no matter what I bring into here. So that's a 5 volt difference from A to B. I want to know how much work is going to be done, so that's what I'm looking for. And I'm going to say that this is now 5 coulombs. So think about it. 5 volts means 5 joules per coulomb. The difference in here is the difference in electric potential from here to here is 5 joules per coulomb. For every coulomb of charge that moves from A to B, 5 joules is transferred. 5 joules of the energy change is 5 joules. So if there's 5 coulombs, and each of those coulombs is associated with an energy change of 5 joules, well, that means that there should be 25 joules of work done. And as a matter of fact, if you were to solve for W, you would do that by multiplying both sides by 5, and you get the work done is 25 joules. Okay? So what that means, 25 joules of energy is transferred. In other words, the kinetic energy increases, the electric potential energy decreases as the particle moves from A to B. Okay, 25 joules of energy is transferred. Okay, that's the basics. We're going to do a few more examples in the next video. Think electric charge and, electric fields and electric potential, think of them as shortcuts. If we didn't have these concepts, you would have to calculate the electrostatic force and the electric potential energy for all these different charges over and over and over again. However, since we have this concept of a field, how much force is put on a charge based on the size of that charge, and how much energy is transferred from for a charge moving from point A to point B in a field based on the size of that charge. It allows us to kind of have a shortcut. We don't have to figure out all the forces and all the energies all the time. We just need to figure out the size of the electric field at a certain location and the difference in electric potential from between 2 points. And again, electric potential is the change in energy as a charged particle moves from A to B divided by how much charge it has. We'll do those examples next time.